from here, so. All right, guys. So really quickly, what are we gonna do today? Today's gonna be a pretty brief lecture. Won't get into too much content, just kind of setting up for the year. So what are we doing in DAV? We'll go over that really quickly. Why FPGAs and Verilog, and then just kind of the logistics of DAV, how we're gonna be handling things this year. And then you guys get some pizza, and you gotta find some friends for teams. All right. So welcome to DAV. My name is Gerard Gravante. I'm a fourth year electrical engineering major. My strengths are that I have a car, which lets me go wherever I want. And then my weaknesses are procrastinating.
I'm Jonathan. I'm a second year C. I'm also one of your DAV leads. My strengths is procrastinating, and then my weaknesses are rain and business.
Alrighty, so what is DAV? I'm gonna go through this quickly because I talked about this in info session. If you can't tell, I copy pasted the slide. So digital design architecture and verification, that is what DAV stands for. So DAV, what you'll kind of be learning about is what are chips? Everyone loves chips. You can become a developer. How to include the pun. So we're going to be teaching you about digital circuits, RTL design, signal processing, graphics basics, test benching, and serial communication. We'll go through what those actually mean when we get there. So overall, in this project, you'll be mostly working with FPGA and system Verilog. Yeah, so throughout the year, you'll be able to make alarm clocks, you'll be able to display graphics on a VGA, and you'll eventually make your own game or a signal processing machine.
Yeah, and for DAV, there's two main tracks that you can take. The first one is game DAV, which is where you get to design a game of your own, where you connect your FPGA with some controller of some sort and then display it all on a VGA. And the game is all up to your choice. The second choice is the more historical track that we have, which is the digital audio visualizer. So here you will take an input from an audio input and then process it, and then finally display the frequency spectrum on a fancy histogram, also on a VGA display. So these are the two tracks that you'll get to choose one out.
So this is an example that me and that kid over there made last year. So these are like all the different steps inside of what we do. So on the left, top left is kind of the code. There are some modules there, one funnily enough named PP, I just realized. So those are the modules. That's called System Verilog. That's the code you'll be writing. Underneath that is kind of the digital logic expression. So I'll kind of go over how to trace through all this and understand it. And then on the far right, that little black box is kind of what it actually looks like on the FPGA chip. You can look into that if you want to. I probably won't cover it. And then that's what it ended up looking like. So it looked pretty cool. So quickly, our DAV timeline for the year. So fall quarters, some logistics. Lectures are hosted Wednesday, 6 to 8. So from now on, our lectures are going to be a little bit more content heavy. So they will be 2 hours starting next week. So, and then each lecture will also have a lab connected to it. So those will be due at the start of the next lecture. We'll talk about that later. But yeah, so our work sessions, I already talked about that. So yeah, our plan this quarter is going to be today. You made it, week 3 introduction. Congrats. Unfortunately, our next lecture got pushed back because I lost rock, paper, scissors, and we don't have a room. So our next lecture is going to be week 5, combinational logic. And then the next lecture will be week 7, sequential logic. And throughout the whole time, we'll be guiding you through system Verilog and test benching. Winter quarter, VGAs. So what is that protocol? How do you display things on a monitor? Signal processing. So we'll derive DFFTs and butterfly units. And then week 8, serial communications. So we'll talk about how to understand a controller and how to use it. And then spring quarter, you'll work on your capstone. So now we'll get a little bit into content. So digital circuits. So what is a digital circuit? So digital circuits are implemented in hardware for specific tasks. So they're pretty much in everything you see. So they're in computers, they're in chips, they're in processors, graphics, CPUs. You need them for Minecraft. So anything that has some kind of logic in it, it is based in digital design. So any kind of processing, so as you can imagine in today's world, it's a pretty prevalent topic. Alrighty, so some topics. So first, next week, we're going to cover combinational logic. Basically, it is instant logic, so there's no memory, none of that you have to worry about yet. And then we'll go to sequential logic, which does have to worry about that. And then we'll get a little into like computational logic. So like how do you combine these two things together? And then memory devices like registers and flip-flops. And then VLSI is taking it a step beyond looking at things from the transistor level, and it's probably something we won't cover. But yeah, if you're interested in digital design, those are like the topics you can look into. Yeah. So what are digital circuits? So at this point, I hope you guys know what a circuit is, but digital circuits store and process informations using states, zeros and ones. So as you may know, circuits typically are like voltage and current, but circuits like to work in logic because that simplifies things a lot more. These states are usually represented by voltage. So even though all circuits are made of voltage and current, we simplify it by kind of rounding up to a 0 or a 1. So if you see down there, there's like little um, squares. So typically what you'll see in reality are like little curves. However, in digital circuits, we kind of round things up so it looks a little cleaner. And then something you'll realize is that they're like, since it's not perfectly straight lines, um, sometimes there's like timing issues. So that way you avoid like getting states at uncertain times, like when it's still rising. But that's something we won't really need to worry about. So common standard for values is 0 voltage, like near 0 is going to be low. And then high voltages near 5 volts is typically our operating range. And that will be considered a value of 1, so on or off. Yeah, so digital circuits basically simplify circuits so that way they're easier to see. So these are like the basic digital gates, logic gates. So each logic gate, at least here on the left side is going to be our inputs, and on the right side is going to be our outputs. And these gates allow us to use those zeros and ones to create logic, to compute things. And we'll kind of get into how that does that. So don't worry if you can't memorize all of this right now. I'll probably guide you through some of these examples next lecture a little bit more in detail, as well as in bigger hierarchies. So the first one's the AND gate. So basically, we have A, B, and Q, where Q is the outputs and A, B are the inputs. So for the AND gate, if you have 2 zeros, a 0. So for the AND gate, basically, if you don't have 2 1s, so if the first input A and the second input B are not 1, then it'll be a 0. So you see, as shown in that truth table, these are all called truth tables. The one in the middle is an OR. So for OR, if A or B are 1, then that means Q, the output will be 1. You can see that in the truth table there. And then NOR, I'm going to skip. So the next one is XOR. I'm going to skip NAND as well. So no, XOR in the middle, what that can kind of be explained as, it means exclusively OR. So basically, it's going to be 1 if OR would be 1 and would be 0. So basically 1 1, for example, is now 0 because 1 1 is 1 for both OR and, but it needs to be exclusively for OR. So that's kind of how you can like simply memorize that table there. And then there's not, so not, if you put in a 0, it comes out as 1. If you put in a 1, it comes out as a 0. And then NAND and NOR are basically an AND and an OR gate with a NOT gate. So the truth tables are flipped. And then you might be wondering why we even have NAND and NOR gates. So a little tidbit for you guys is that NANDs and NOR gates actually require less transistors than ORs and ANDs. So they actually tend to be simpler or like more efficient. So that's why we're not just showing you ANDs and NOTs, because NANDs are actually more efficient and you might want to like try to design with those. Yeah, so but those are the basic building blocks. Next lecture, we'll actually go through how to create logic using them and create computation. This here is a simple full adder, so this allows you to do addition. So all computing devices have these. You'll probably make a few of these by the end of DAV. So yeah, we can build more powerful circuit from those gates.
Yeah, so as Gerard said, using just these very basic logic gates, we could build really powerful digital circuits. And so like where we find digital circuits in the real world is CPUs, ASICs, FPGAs. These are the main three ways in which computing is done. CPUs, I'm sure you guys are all familiar with. They're used for general purpose computing. All of your laptops, phones, all of these have CPUs. And they follow a series of instructions that you can program. And so they're very flexible. ASICs, on the other hand, they're very specialized devices that do one task extremely quickly. And so if you want to do like a very specific task all the time, very fast, then you want to use ASICs over CPUs. And another con for ASICs is that it's extremely costly to design and also fabricate this chip. Oftentimes fabricating the chip may take multiple months and may take millions or billions of dollars to fabricate. And so that's why we have FPGAs. So FPGAs are similar to ASICs, but they're designed to be reconfigurable. So you can kind of think of it like an ASIC, but you can remap all of the gates so that you can have different functionality. And so because of this reconfigurability, FPGAs are often used to test ASICs before you actually deploy them or like fabricate. What does ASIC stand for? It's a good question. Application-specific integrated circuit.
Yeah, that's right.
Let's go. Okay.
Any other questions? Feel free to raise your hand whenever.
Yeah.
Sounds good.
Okay. So now I'm going to go over a little more about the FPGA architecture. So the FPGA doesn't actually contain any logic gates like OR and NAND or other logic gates that Gerard explained earlier. Instead, they're actually made up of lookup tables. So you can think of lookup tables as like a truth table that will allow you to simulate a certain Boolean function. For example, if we want to implement the OR gate on an FPGA, rather than actually having an OR gate in the FPGA, we use this lookup table, program the zeros and ones, as you can see here, the A and Bs, and also program the Qs to correspond to an OR gate. And that's how you create logic in FPGAs. Yeah. But just using lookup tables, you won't be able to do a lot because there's no memory component. And we'll go more over into this in sequential logic and later lectures. But FPGAs combine lookup tables, which you can, again, think of it like a truth table, flip-flops, which we'll go over is like some sort of memory component, and multiplexers, which allows you to select one out of many different bits. You kind of think of it like an if statement. And so with these basic components, grouping them together into a configurable logic block, which is what we call it, you can build a lot of really, really powerful circuits. So in an FPGA, there's a lot of configurable logic blocks. And as you can see here, here's just like 6. And all of these are interconnected with wires that we can also program. So maybe like to say this top left interconnect, we could map it so that the logic coming out of one configurable logic block can be remapped to another configurable logic block. And so using multiple of these configurable logic blocks and also the interconnects, we could build any circuit that we can imagine pretty much. So here's a little overview of the FPGA that you guys will get. So we're going to be using the BASIS 3 board. It's a little small, I know, but basically this diagram goes over all of the different components that your FPGA will have. So the FPGA is actually just that little square right above the BASIS 3 symbol. Everything else is just all like different components or like I/O that you connect the FPGA to so that you could more easily program it or utilize like peripherals such as a microphone or a controller or whatnot. In the interest of time, I'm not going to go over all of these, but if you're ever like interested in like what one specific thing does, you can just ask me.
Yeah, so that's basically the hardware we're going to be using. So how do we actually use it? So the FPGA, we're going to program it, but we're basically going to use a language called System Verilog. So one thing to note is that System Verilog is not a C programming or is not a programming language. It's what you'd call an HDL, a hardware description language. So when you create programming languages, these languages are basically instructions that your computer will like understand using like an ISA, and then it'll get like be brought down to like machine code and then like all the hardware will understand it. We're basically skipping all those steps and we're going to directly translate the hardware in our programming. So very important distinction that our code is changing hardware and we're not like, it's different. So yeah, we're basically making digital circuits by coding. So how this is actually going to work. So first we're going to write the behavior code. So this is probably the closest to the higher level programming. So normal programming you'll see. So instead of manually assigning the gates, you'll use system Verilog to describe what you want to see. And then from there, after you've wrote the behavior, the code will get translated and like synthesized into like Boolean functions that can be described by logic gates. So if you remember in the picture from before, that was like kind of like the string of green gates that you saw earlier. And then the FPGA is reprogrammed. It reprogrammed itself by re-encoding the lookup tables that Jonathan explained and the routing. So that way the digital circuit is realized. And yeah, that's how you do it. So yeah, that was pretty much it. It was just a quick introduction. Next time we'll get a lot deeper into content, but now we're gonna go through some logistics of the year. So also make sure to check the syllabus and the acceptance email, as well as the Discord message with all the links and stuff, because yeah, please do the things that we said so we don't have to hunt you. Yeah, so some DAV logistics. The first thing I will say is that we had 130 plus applications this year. So that meant we cannot accept everybody. If that's you, I am sorry, but glad you're here anyways. So yeah, we cannot change any of these decisions, unfortunately. Do try to take it easy on us. So if you're not accepted, or if you know someone who was not accepted, we are opening the ability to audit the project. So what this means is showing up and watching the recordings. All these lectures are recorded and posted publicly on the DAV Discord channel, as well as the labs. So all of that is public. However, if you are not a DAV student, please do not come to the work sessions. We will not have the bandwidth to help you. There will also, you will not be assigned to a team. You also will not be able to check in. Like the leads will not be checking in on you. Also, please do not eat the food. That's not in our, that's not, we did not budget for more than the people we expect. And then we will probably receive less help with labs. And then for these people, do not, please use the equipment during me or Jonathan's lab hours. Currently, those lab hours, I'm there. Any of you guys could come to these lab hours, by the way. I'm there 3 to 6 on Mondays. Jonathan's there 1 to 4 on Wednesdays. So please use the equipment during that time. And then, yeah, I'm saying this with a grain of salt because I can't promise this at all, but you can be accepted later if there are other DAV members struggling with commitment and you are shining and doing all the labs. So we'll probably reach out in winter in like the DAV channel being like, are there any auditors still alive? We have spots. But yeah, so no promises there, but it is possible. And then yeah, if you're an auditor and end up making a capstone, you can also pull up to the showcase and to be decided, but I think you should be able to run for lead as well if you actually finish the project. So yeah, yeah. So after this lecture, oh, I think, oh,
Yeah, so after this lecture, we're gonna post a form for all of you to make your teams. The team is gonna be a maximum of 3 people per team, and only one person needs to fill out the form. If your team has 3 people, then only one person should fill out the form. If your team has 2 people, only one person should fill out the form. If you're by yourself, you should fill out the form. And this is due by Friday, October 17th, so in like a few days at 11:59 p.m. If you don't have a team, don't worry, we'll have a social right after this where you can get to know other DAV members and potentially form teams from there. Also, everyone in DAV, as we iterated in a project info session and other times, that DAV members must submit a deposit of $50. And we'll return this upon when you like finish your project or labs. So for the fall labs, if you finish all of them, we'll return 15. If you finish all the winter labs, we'll return another 15. And then if you finish the capstone in the spring quarter, then we'll return all of it. And so please get all of your deposits in by Tuesday, October 21st at 11:59 p.m. As for the DAV deposit structure, we prefer Venmo at IEEE at UCLA with the following description as shown on the slide. However, if you don't have Venmo, we're open to Zelle or even cash. And also, if you have for any reason you want like a lower deposit amount, we won't ask you any questions. It's not non-judgmental, and we'll just grant you like a lower deposit or no deposit at all. And yeah, because this deposit is not really for us to earn money, but rather to like motivate you guys to get all of your labs, capstones, all done. Any questions on the deposit side?
Wonderful.
Oh yeah, also auditors don't need to do deposits. I forgot to mention that.
Yes.
I think that's fine. Yeah, and also in addition to the deposits, every student must complete a lab safety coursework before you can work on DAV. This is similar to all IEEE projects. So we're gonna send out more information later on Discord, but basically you have to visit the UCLA WorkSafe website and then do the following 4 lab safety workshops. And then after you're done, take a screenshot of your certificate and then submit it to a form that we're gonna attach later. And this is also due on Tuesday, October 21st.
Okay, so due to how many project people we actually have, we're going to have some restrictions on the usage this year. So first things first, DAV kits will not be allowed to be taken outside of the IEEE lab. So unfortunately, due to the large amount of people in the project, some kits may need to be shared by 2 teams. At least for the first quarter. During winter, we'll probably be able to issue out during winter and spring, it's quite possible you'll have your own kit. But at least for fall, some of the kits might be shared, so all the kits must stay in the IEEE lab. Yeah. So for the DAV members, the auditors have a little bit more restrictions, but for DAV members, you are allowed to use it whenever. So even if Jonathan and I are not there, just come into the lab, use it whenever, but just make sure to keep it in the lab because losing a kit will be quite sad. We will still be assigning kits to teams. We will be creating our master document with all the teams after you guys submit your forms or your team form. So one thing to note with that, if the teams that are sharing a kit are both using it, but like there's another kit available, you can just use another kit. It's fine. So yeah. And then spring quarter, oh, I already mentioned that. Yeah, there's a syllabus. I've shown it out like 10 times already, so. So yeah, your first assignment for this week will be to install Vivado onto your computers. Jonathan has kindly made documentation for that. So check the DAV links channel. It should be there. Should be pretty straightforward. Vivado is a chunky program, so be prepared for that. But it should be pretty straightforward. However, if you have a Mac, not so much. You can set up a Windows virtual machine. I have no idea how to do that. I don't use Macs, so good luck.
I have a Mac, so I can hopefully help out, but
Wonderful.
we'll see. Yeah, we'll see.
Tim, not me. Okay, so all right. So if you're struggling with install process, just ping one of us. And then yeah, if it's Mac, definitely him. So another thing, we have DAV laptops available. So if you're struggling to download it, those DAV laptops are ready to go. Yeah, we will be posting Lab 1 soon. By soon, I'm hoping by the end of the weekend. And then since our lecture got moved an extra week, you guys have less time to work on Lab 1 after Lecture 1 or Lecture 2, I guess. So it might be a good idea to start looking at it a little bit, but since you don't know the content yet, don't expect to be able to do all of it. But yeah, it will be due at the end of Lecture 3. So,
oh yeah. So just a general overview. Week 4, do all of the things that we said earlier, like the deposits, the lab safety stuff. Install Vivado, and then get to know your teammates. Week 5, we'll be holding another lecture in this exact room where we'll teach combinational logic. the basics of system Verilog, and maybe a little sprinkle of computer architecture. And then week 6, we'll have our first work session of the year. It's going to be at 6 to 8 on Wednesday as well. But we don't have a location set for now, so we'll notify you guys later. And so like here's a great time for if you have any trouble with installing Vivado or on Lab 1, it's a great time to talk with us, and we can maybe help you out with the lab or installing Vivado.
Yeah, so I know y'all are so excited, but wait for me to spew nonsense at you until week 5. Today will just be pretty much logistics. Okay, before we get to some fun stuff, there's something I want to add. I'm just gonna, you guys can watch me add it, unfortunately. But I want to make some guidelines on, so since there's like 100 of you, it's gonna be really hard to keep up. So if you have done an IEEE project, you know, or if you haven't, now you'll know that we typically have team channels. So all communication will have to go through to the leads will have to go through the team channels. So what this means is if you DM me and Jonathan after the team channels are made, I'm not going to respond to you. Basically, this is avoiding me from getting bombarded by auditors as well, who I did not sign up to be bombarded by. So you guys can though. So if you in the team channel, feel free to add us as much as you want, and we'll help you out there. So yeah, that's pretty much it. Um, I want to make this distinction because like there really are 100 of you, and we want to be able to help you as much as possible. So in order to make that happen, please keep in the team channel so we can like manage all like 30 teams of you guys. Also, that way you guys make friends. Okay, so DAV merch drop. So I really want DAV merch. We're thinking of maybe pushing out sandals, which would be kind of cool. But like, so
You'll understand later. You'll understand later. Yeah.
so like if you have any burning desires for design, you can DM me. I'll respond to that DM, by the way. So if you have a design, I'll respond to that. And then that merch will most likely be free for winter survivors. So yeah, more incentives for you guys to actually finish. Talks are kind of that'll be tough. That'll be tough. All right. Yeah, so that's pretty much it for today. So, bye then.
Okay.
Yeah. I feel like we could have put a little more. What's okay?
You need your pause recording.
Yeah, that's a good idea. Oh, God. We should.